All right, welcome. In this video, I'm going to be telling you about parametric equations. So parametric equations are a set of equations for x and y in terms of an independent variable like time, t, that will trace out an oriented curve in the xy plane. So before this point, our functions took in a variable x, we did whatever f was to x, and we got f of x, which was y. But now we're going to start off with a time variable. Oftentimes that's what we're going to consider t as time, but it doesn't have to be. And then we're going to do f to it, and f is going to give us back an x coordinate and a y coordinate. And so oftentimes we'll see these listed like this, as some function of t, comma, some other function of t, but we can just think of it as, the x, y coordinates of the curve. But if we think about it, we really do already have some experience with parametric equations. These equations, x equals cosine t and y equals sine t, we know what that traces out. We know that traces out the unit circle. And not only does it trace out the unit circle, but we have kind of like an idea of the orientation of it. We know that, this is a little rough, but it's all right. Assuming this is a circle with radius 1 centered at the origin, we know that it starts at 0 and then it kind of goes in this counterclockwise way to pi, and then to 3 pi over 2, and back to 2 pi, and beyond 2 pi, it keeps going around the circle. So we've seen this before. This is the unit circle. And before we keep going and start doing some calculus with these parametric equations, I just want to show you that you can graph these using a graphing. So if I go into my calculator and I go to the mode and I switch it to parametric mode, I can type these things in. But as I'm doing it, I just want to let you know that this is never the thing to do in AP Calculus. This is never how we solve any problems in AP Calculus by going into parametric mode. This is only something that I'm just showing you that you can do. All right, so see, I've already got it into x of t and y of t here. I'm going to set the window, I think it didn't say here, but the t window, we need to have t between negative pi and pi. So I'm going to actually type that into the window. Negative pi to pi. Okay, and then this is, I don't think that this is going to be a good x window. I think we need a lot more room to see this thing go. Okay, and then when we graph it, it makes a heart. Okay, so we can say that, hold on, let me try that again. Okay, I kind of lost the orientation of it. Watch it. Yeah, it started from the bottom and then it traced out. So I would say that the orientation in terms of increasing t is going to be this way, because we saw the calculator draw the curve that way. We can also do this by hand. So I'll just real quickly do a 0 to 4, wait, no, not 0. T, and we're used to making a 2-column chart, right? But now x and y both depend on t, so we would need to make a 3-column chart. But we're just going to do 0, 1, 2, 3, and 4. Make a little more room in our table. And then we're just going to fill in x and y. So this is going to be 4, 1, 0, 1, 4, and y would be 3 minus 0, 3 minus 1, 3 minus 2, 3 minus 3, and the absolute value of 3 minus 4. Okay, so I'm going to just kind of, I'm going to need x at 1 and 4, y at 0, 1, 2, and 3. And now I'm just going to start plotting stuff and connecting the dots. So 4, 3, 1, 2, 0, 1, 1, 0, and 4, 1. Okay, I know actually that this is going to be a sharp corner, but you don't need to worry about that. It's a sharp corner because of the absolute value of 3 minus t having a sharp corner in its graph, but that's going to be approximately what that graph looks like. We can do that by hand, right? All right, now let's do some calculus. So if we want to find the slope of the tangent line to one of these parametric equations, what we're going to do is we're going to find dy dx by taking dy dt and dividing it by dx dt. Okay, it pretty much works like you would expect. Okay, what we need to do is we need to just find dy dt and dx dt by taking the derivatives of y and x respectively. So I know that dy dt, which is what I get when I take the derivative of y with respect to t, is going to be the derivative of 2e to the t. Okay, so I'm taking the derivative of 2e to the t, and I'm getting 2e to the t. Okay? Then I need dx dt. Dx dt is going to be where I take the derivative of x, and x equals t to the 2 minus 1. So the derivative of that is just going to be 2t. And since dy dx is y prime over x prime, or dy dt over dx dt, I'm just going to say that dy dx is 2e to the t divided by 2t. Okay, and there's some of the easier multiple choice questions on this are related to just dy dx. We just take the derivative of y divided by the derivative of x. All right, now let's work a particle motion example and also talk about writing these things as vector functions, right? That's something I haven't done yet. So if the position at time t is given by x equals t to the 3 minus t to the 2 and y equals e to the 2t minus t, we can write the position of the function as a vector. Okay, and while in general, probably most vector-valued functions in other classes, you're going to call them r of t, that's not really something that you see in AP calculus. So we'll just call it position at time t is given by, and we can put little pointy things on it to indicate it's a vector, but it's just x, t to the 3 minus t to the 2, and y, e to the 2t minus t. And we can take the derivative of these vector-valued functions just exactly the way we would expect. Okay, we're going to just take the derivative of each of the components separately. Okay, so we know that v is equal to the derivative of position, right? And that doesn't change if we throw these vector things over them, right? So that means that v of t, yeah, that's what we're looking for, the velocity vector at any time t is going to be, I'm just going to take the derivative of t to the 3 minus t to the 2. That's not going to start with t, it's going to be 2t. And taking the derivative of y with respect to t. The derivative of e to the 2t is going to be e to the 2t times 2 for the chain rule, minus 1. Okay, and that's our velocity vector. Find the acceleration of the object at t equals 1. Well, the acceleration, we know that acceleration is equal to the derivative of velocity and also equal to the second derivative of position, and that's still going to be the same if these are vectors. Okay, so I know that a of t, I'm going to just take the derivative of v, and I'll have 6t minus 2 and 4et. And then I'll just plug in 1 to get a of 1. And so that would be 6 minus 2 is 4. And then 4e to the 2 times 1 would just be 4e to the 2. Okay. Now, the slope of the object's path, that's going to be dy dx. Okay, you see slope, that means dy dx. Okay. And we know that's equal to y prime over x prime. But we already have y prime over x prime in the velocity vector. And I guess if I want at t equals 1, I'm going to have y prime of 1 divided by x prime of 1. So I can just do that kind of first. Okay, over here, I'm going to say, okay, y prime of 1 equals 2e to the 2 times 1 minus 1, right? I got it from right there. That's the y component of the velocity. That's also dy dt. Okay. And then I'm going to divide by x prime of 1, which is what I would get when I plug in t equals 1 into the x component of velocity. And I'll get 3 minus 2 is equal to 1. Okay. And so I would say that the slope is 2e to the 2 minus 1. Another thing we can do with dy dx, or the ability to take derivatives of these things, is figure out where a parametric curve has a vertical or a horizontal tangent. Okay, I'm just going to real quick draw you a picture of a curve that's got a vertical tangent. You know, maybe it's got some orientation here, but at this point, the tangent line is vertical. If you think about the motion of an object passing along that curve, at the point of vertical tangency, y is increasing, so I'll just say y is changing, but x is not. X is constant. Okay, and if y is changing, that means that dy dt, or y prime, is not equal to 0. But if x is constant, we know that a constant, well, really what that means is that it's not changing and its derivative is 0. So that's where I would say x prime is equal to 0. And as a result, the key aspect of a vertical tangent scenario here is going to be that dy dx is equal to number divided by 0. But we've actually already seen that in this course when we were doing implicit derivatives. So we really know that as long as y prime is non-zero and x prime is 0, we'll have a vertical tangent. So, in terms of dy dx, we're looking for a number divided by 0. But in terms of actually solving and finding the places where the tangent is vertical, we're going to look for the zeros of x prime. Now, technically, we also need y prime to be non-zero, because if they were both 0, we most likely are sitting at a sharp corner. But in AP Calculus, we don't really deal with that scenario besides to say that an object that's moving is at rest. And we'll deal with that, I guess, next time. Now, for the horizontal tangent, I'm going to really do the same thing, and maybe I'll have it going, like that, going what we would consider to be backwards. And, you can see where I'm going with this. This is where x is decreasing, so x is changing, meaning x prime is equal to some number, and y is staying constant, so y prime is equal to 0. And as a result, I have dy dx equaling 0 divided by a non-zero number. But again, we've seen this happen. We know that a horizontal tangent is equivalent to where dy dx equals 0. So if we're, algebraically solving for these points, our thing we're looking for is y prime equals 0. Again, because we're going to start with that. We're going to make sure that x prime is not simultaneously 0, but in the back of our mind, we know that doesn't really happen in AP Calculus. Okay. And that's how we deal with vertical and horizontal tangent scenarios. All right, now let's do a quick example before we move on. Where does this function have a vertical tangent? Well, I know that a vertical tangent happens at a place where x prime of t is equal to 0. And I know that this is x of t. So I'm going to say, well, x prime of t would be 3t squared minus 2t equaling 0. And I'm going to factor and solve. So I'm going to factor out a t, and I'll be left with 3t minus 2. And I'll see that this product is equal to 0 when one of the factors is equal to 0, which would happen when either t was equal to 0 or when t was equal to 2/3. Now I need to also, check that y prime is not simultaneously 0. But, in AP Calculus, we probably don't have to worry about that scenario because it just doesn't come up. Okay, so you can go ahead and take y prime, pause the video, take y prime, check t equals 0, check t equals 2/3. But I'm just telling you that y prime is not going to be 0 at those places, so I'm going to choose answer choice C. All right, now let's talk about the second derivative of y. Okay. If we want to know the concavity of one of these parametric equations or something, we're going to need to find the second derivative of y with respect to x. We've done that before, and up until now, the f double prime and the second derivative of y with respect to x is the same thing. But now it's going to be slightly different. So if we want to find the second derivative of y with respect to x, what we're going to do is we're going to take the derivative of dy dx, and then we're going to not forget to divide by dx dt. Now, the reason why we need to divide by dx dt is, well, it's something I'm not going to go into on this video. If you wanted to know why, it's related to the chain rule and I think the quotient rule, and I've got a video explaining all of that, but I'm just going to, show you the formula and work with the formula in this video. I'm not going to be explaining why it works. Okay, so let's do a quick example. All right, so here we've got x and y given in terms of t. We want to find the second derivative of y with respect to x. Now, I'm going to kind of draw the comparison between this and the second derivative of f, or the acceleration vector, here in a minute, but we see that fraction, d2y dx2, right? We know that it means that we're going to take the derivative of dy dx and divide by dx dt. So let's get to it. I'm going to start with y prime equaling 3t squared and x prime equaling 2t, which gives me dy dx equals, well, 3t squared divided by 2t. Okay, now eventually I'm going to have to take the derivative of dy dx with respect to t, right? So I could leave it as 3t squared over 2t, but then when I took that next derivative, I had to use a quotient rule. So this is a situation where we're actually better off doing the simplification. Okay, they aren't many in this class, but this is one of them. Okay, so I've got this. I bring in the formula, and then I'm going to do that. So I'm going to say this is the derivative of dy dx is the derivative of 3/2 t. The derivative of 3/2 t with respect to t is just 3/2. And then I'm going to divide by dx dt. Okay, we know that dx dt and x prime of t are the same thing. And so I'm just going to divide by 2t. And if this was a multiple choice question, I would need to be able to pick out the right answer, and I bet that they would write it like this, right? With the t in the denominator. Okay, and that's an example of us finding the second derivative of y with respect to x. All right, to contrast, we've got the second derivative of f with respect to t. And when they ask for that, that's where we're just going to take the second derivative of this vector valued function, and the second derivative of that's going to be a vector. Okay. So, we know that f prime of t is going to be equal to, okay, we can take the derivative of 2 to the t. That's 2 to the t multiplied by natural log of 2. And 1 over t, well, we can just think of that as t to the negative 1 power, so it would be negative 1 t to the negative 2 power. Okay, and then we could get f double prime of t by taking the derivative of this. And, okay, the derivative of 2 to the t times log of 2 is going to be, well, again, 2 to the t, but I'll have another power of log of 2, so I'll just maybe square that. And then I'll take the derivative of negative t to the negative 2, and that will give me positive 2t to the negative 3. Okay, so if they ask you for f double prime or the acceleration or something like that, that's where it's going to be a vector. Okay, and yeah, I'm trying to, well, I don't know what else to say. Versus if they ask for the second derivative of y with respect to x, like explicitly using that fraction, or they ask you about the concavity, that's where we'll use the new formula. Now, the last new piece of information I've got for you today is how to compute the length of one of these parametric curves. So suppose this is, the point that corresponds to t equaling t1, and this is over here the point that corresponds to the point time t2. And we want to find the length of this curve. What we're going to do is we're the exact same thing when we found the arc length for a regular y equals f of x curve. We're going to cut it up into a bunch of little short pieces, find an expression for the length of one of the small pieces, and then add them all up. Okay. So we know the drill. We're going to turn this into a right triangle. I'm going to say this is a small piece of arc length. This is going to be delta x, and this is going to be delta y. We also know that delta p is the square root, the length of delta p is the square root of delta x squared plus delta y squared from the Pythagorean theorem. So I can say that the total length is the sum of these small lengths, which is the same as the sum of these square roots of delta x squared plus delta y squared. But I know that this wants to become an integral eventually, right? And an integral is a limit of a Riemann sum. And so we're going to be integrating with respect to time, pretty clearly. That's the independent variable in these scenarios. And so we're going to need a delta t on the outside, right, to turn this into a Riemann sum. And so I'm going to multiply by a clever form of 1. Okay. And then I'm going to combine these together, use a little exponent property, and then I'm ready to go. I'm going to let my number of pieces of arc length go towards infinity. I'm going to let their respective lengths go towards 0, and then this is going to become the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared dt. So we take each of the x derivative and the y derivative, we square them, we add them together, we take the square root, and we integrate it. That's how we find the arc length. So, maybe I'll even highlight this, because this is the formula that we now just need to know at a moment's notice. And, much like the other arc length ones, this is probably going to be something you have to use a calculator for or choose from a list of integrals. And kind of now the responsibility, in addition to knowing the formula, is knowing when do I use this formula versus when do I integrate 1 plus dy dx squared. And it's, does your function depend on t? Is it a parametric equation scenario? Or is it just what? Old-fashioned y equals f of x? All right, we can do a quick example of this. Find the length of the graph of f of t from 0 to 3. Okay, so what we're going to need, our ingredients are going to be x prime of t and y prime of t, and then we're going to put them together in an interval, and we're going to need to use a calculator for it. So I'm going to say, all right, x prime of t, I'm going to take the derivative of this thing, right? So it's going to be the derivative of the outside multiplied by the derivative of the inside, while leaving the inside the same. And y prime of t is going to be, all right, the derivative of the outside is, well, the derivative of e to a thing is e to that thing, multiplied by the derivative of the inside is 2. And we've got an expression for x prime of t and y prime of t, right? And I know that the length that they're asking for is going to be the integral from t1 to t2, that's 0 to 3, the square root of dx dt squared plus dy dt squared with respect to time. And I'm going to bring in a calculator. And notice I'm taking this back to function mode. And I'm going to integrate in radian mode as t runs from 0 up to 3 on square root of 3 cosine 3t. We'll use the x button, it makes the same thing. Close off the parenthesis and square it, plus 2 e to the 2t, square that, and integrate with respect to t. Let it think, and I get 402.962. Okay. And that's how we compute one of these arc lengths. I think that's all I got for you for this video.